Okay, good morning, good afternoon, good evening. So today we're going to continue with what we were doing before. I think what I want to do here is turn this down. And I think I want to just kind of outline in pseudocode what it is that we will be doing. I don't think I've done that yet, but we can start to do that now. So every second, some period of time, which we can define, every interval, add a potential, or given some chance, add an event or publish, and then this is for each node. Given some chance, publish an event. Okay, so now that's publishing those events for a random. Okay, and then I guess who owns the time? This could be an event generator. I think that's the way to do it, and then we can figure out how to manipulate the characteristics of the event generator. So for every interval, for each node, given some chance, publish an event. And there's a few things to that, right? So what could go wrong with publishing events? And what are some of the things? The event may not be published. The event may take time to publish. The node. So let's I don't want to get into too many of these details, I suppose, because there's a lot of things that could go wrong. And maybe I'll just model this out and think through it later. So publish an event, and then what? For every interval, then we want some other thing. For each form. So there's actually a few things. For each node, given some chance, perform an activity. Okay, and then for each, if the activity completes successfully, fire an event. Okay, so what am I trying to mimic? Right now I'm trying to mimic network latency, which would mean out of order events. So it's not really about the activity. It's about the processing time for the activity and the fact that the sequence of those events may arrive at a consumer out of order. So it's effectively, what's the okay. So here is what I want to read. This was a long time ago. So exactly once semantics are possible, here's how Kafka does it. I'm thrilled that we have hit an exciting milestone, period. Oh no, the Apache Kafka community has long been waiting for. We've introduced exactly once semantics in Kafka in the 0.11 release in Confluent Platform 3.3. In this post, I'd like to tell you what Kafka's exactly once semantics mean, why it is a hard problem, and how the new idempotence and transactions feature in Kafka enable correct exactly once stream processing using the Kafka Streams API. To read the other posts in the series, please see, so there's transactions and enabling exactly one in Kafka Streams. Exactly once is a really hard problem. Now I know what you were thinking, exactly once delivery is impossible. It comes at too high a price to put to practical use, or I'm getting this entirely wrong. You're not alone in thinking that. Some of the industry colleagues recognize that exactly once delivery is one of the hardest problems to solve in distributed systems. Yes, okay. While some have outright said that exactly once delivery is probably impossible. Now I don't deny that introducing exactly once delivery semantics and supporting exactly once stream processing is a truly hard problem to solve, but I've also witnessed smart distributed systems engineers at Confluence work diligently with the open source community over a year to solve this problem in Kafka, in Apache Kafka. So let's jump right in with an overview of messaging semantics. What is exactly once semantics? Messaging semantics explained. In a distributed publish-subscribe messaging system, the computers... So this isn't about sequencing yet. I was actually thinking probably about Datomic. No, I'm thinking about Kafka. It should have in order guarantees as well. So I'm wondering if I care about this. I really don't care about this. I only care about contiguous messages. And if I get more than one, I can just drop it. So I want at least once semantics. Yeah, so this is very interesting, but not what I care about. So I don't want that. Okay, here we go. So this is how to use it. Okay, so this is the major, I guess, blog post about Kafka, but where... each ordering of records. Okay, so this doesn't solve the problem, I don't think, because this queue means that based on when it was provided to Kafka, which doesn't solve the problem of it could be provided to Kafka out of order, semantically. So we have event time, which we can use here. So there's... So I guess the experiment is, yeah, every interval for each node given some chance perform an activity. And the activity will take some duration to complete. And the big thing here is if the activities themselves in sequence are not completed within the time frame you would expect, then you'll produce errors. So that's fine. And I can map this on two terrains, I guess. A logical time and a chronological time. First what? And clock time or chronological? Okay. So I probably mean that. And clock time is, I guess, an arbiter of relativism, or absolute value, rather. So, okay. So I can have like a clock time visualization, which would be just milliseconds as the x-axis, and the y-axis would be this kind of like stream. So let's draw this, I guess. Okay. And great. And then, okay. Cool. So what I want to do, and I probably need to move this at some point. Maybe I move this here. We'll figure those out later. But I think that makes much more sense so that I can actually draw. I feel like doing all those other things is secondary. So draw, is it drawio.com? I feel like that's just a really good domain name. No. Wow, they really get all the domain names. Okay, so here we go. And what I would like is kind of node A, node B, node C, and there would be some indication of time, but I don't think it matters to have like a scale. Maybe there is a scale, like there's something down here, and it's like, or 0. I don't know how to undo. Okay, so you have 0. And then you have like, let's say the interval is 1 second. So let's say 1 second. And then 2 seconds. So there's some chance that like A has an event, let's say. And it's going to publish. So what do I want to do with these? I don't want to publish to B and C. I just want to have the event, and then the event is going to last for some period of time. So it's going to like, let's say it lasts like for that long. And let's say we have this event here, and then we have like another event here and another event here. So an error would occur if this event, I don't know if the highlight's going to work. No, it's not. But like this would be an interesting situation where this C event, and maybe I can do this. Like that. Okay, so what are the issues with this representation? So I guess the first issue is these, is there a way to like, these are out of order. So how would that play out. Now, this is the visualization for the events themselves, right? And this would just keep going, and maybe it doesn't matter that you see 2 seconds, and then this would be like 1 second, 2 seconds, and the visualization itself should have like an end for each of these, and that could just be and then like if you highlight, it would say like whatever. Something like that. I don't know. For debugging purposes, and you would need a play, pause. Wow, I don't know what pause is, do I? Pause and stop and speed, let's say. Right, that would be an interesting way to explore generating events. And then you would need some way. Is that a good representation of just event processing? I don't know why I put those in. I don't know why I put those on these lines. Can I move this? Yeah, I need to move this guy. And then draw. Okay. So something like that. And okay, so we have start and end durations. We've got all these events. The thing we're missing is mapping these events to when they get communicated, which is where the latency is introduced. I don't like this visualization at all. Like, this is good to represent, I guess, whether things are working correctly when we publish these events for a specific duration. But I don't know how to, and like, can we minimize a little bit of this stuff? There's too many things going on here. So we can get rid of that. We can get rid of that. That looks a bit cleaner. And this doesn't matter too much right now. It's just interesting to know. And then I guess we don't even need that. So it would just be that. And like, this is interesting, but I guess it doesn't, that doesn't even matter. Okay, so that cleans things up a little bit. And then we have like that. And actually the opposite is what I'd like to do. This guy goes away and that guy goes away. Okay, so that's better. But what do we do when we want to map the events finishing and starting to some kind of linear sequence? Because this is almost too clean. Like, the thing that makes this messy is what's happening in C. So we need some way of like flattening this. Like I can imagine you just kind of bring everything down and you've got a new representation of the events. And that actually is, oh yeah, because the dark orange is representing that the second event starts and finishes before the first event completes. So they would be out of order. You get the second event finishing. So there might be a representation which is like, I'm thinking like a chart. Something like that. And then these are just events, right? So this is saying like A started, C started. This is saying B started, C2 started, I guess. This is saying C2 finished. And then this is saying A1 finished, B1 finished, C1 finished. So those dots could represent like the events that happen in a contiguous window, like every 10 milliseconds or something. And they could stack up based off of that. And would that help? Maybe. Right, because then there's one more diagram, which is if I were to want to know what the current state at any moment of the events would be, it would be like, let's say here, and maybe this is better than dots. So A1, C1, this is B1 and C2, and then this is C2, some way to indicate that it's ended, maybe a different color. I don't like that. Maybe just C2 and then highlight. Yeah, let's try that. So then that's C2. That's, I can, A1, this is B1, and this is C1. And then the highlight would be ending, ending, ending. But, I guess what I'm really looking for, yeah, because I don't want to get back to this. I feel like I'm not doing too much more with this. Because do I get final ordering? I do. I guess here I get final ordering. So maybe that's what I want. Is I have these coming out of order because I have C2 completing, A1 completing, B1 completing, and C1 completing. And you can see here that C1 starts. Is that the best representation though? Like this is really good because that shows me what I actually care about, which is what is the order that we end up with. And I don't care about the other part. So I think the top diagram is useful, and then maybe the bottom section is useful. Is my guess. I'm still missing something though. I don't think this is good enough. There's like, this is traces, I guess, is what I'm looking at the top. And that's like a Gantt chart that could be represented. And I don't know if it matters which node. Like, one of the problems I think with this diagram is this stuff. Like, I don't really care about what node starts the event. That's only relevant if I'm looking to understand in the confines of an individual node whether something is in order. But like, I can simplify the problem to be just have events started or stopped and not consider nodes. Like, I think nodes is complicating things. So I could have like, right? And if I have just one node, oh, that's so small. Then what problem can I represent? I can represent overlapping events like this, because C is the only real thing. So like, let's forget about everything else for now. Right? And then maybe this is like irrelevant too, because now that's all represented. So like, that's an issue, which is that the second one completes before the first one completes. And I guess the question is, would I have enough information? Oh, but it's a distributed system. Like, one of the complexities is that it's in a distributed system. But I guess, yeah, because you can have concurrent messages. Okay, so fine. So what would I really want to know? I guess I would want to know whether the truth of what I understand, if these are facts about like one entity, right? Because I think maybe that's how this can work, is if everyone's trying to say the same thing, like A is saying the light is on, B is saying the light is off. This is the general's problem, right? Yeah, so what is this? Byzantine general's problem is a game theory problem which describes the difficulty centralized parties have in arriving at consensus without relying on a trusted central party. Maybe I'm looking at Raft. Like, in a network where no member can verify the identity of other members, how can members collectively agree on a certain truth? The game theory analogy behind the Byzantine general's problem is that several generals are besieging Byzantium. They have surrounded the city, but they must collectively decide when to attack. If all generals attack at the same time, they will win, but if they attack at different times, they will lose. Oh, that's interesting. The generals have no secure communication channels with one another because any message they send or receive may have been intercepted. I don't know if that part is as useful. How can the generals organize to attack at the same time? The security thing adds like a wrench, and send false messages. Like, that's too complicated. That is almost too complicated. Go back to this. So let's assume all of the messages are in good faith. That's less relevant here. If they come out of order and one hasn't ended, which I think is the issue, is C1 hasn't ended. So if we don't have a started event, we don't even know that there's a C. Like, the real issue would be this. If we had, let me erase everything else. See, in this, if we had a started event that needed to talk to broker. Oh. Right. And if this message didn't get to the broker before this message did, right? And let's say both of these got there. You don't even need both to get there. You just need that one. Let's say we're only concerned with finish events. And if that's true, then can I even say something further, which is really just this, that like this is definitely going to get to the broker first, the finish event, which would imply that at time like t here, if we were to represent something, we would represent it out of order because of the delay in processing C1. You can't fix that because we don't actually have the results of C1 yet. You can send the messages, the start messages, which would potentially show gaps, like you can simplify that problem, but you still have the fundamental problem, which is this. So I can get rid of the finish messages. Or actually, does that solve it? No, it doesn't. So we have this problem. Wow, not having the thing I need on the screen is like really weird. So if the initial C1 can I do? No, that doesn't work. Okay. So if the initial C1 message started is sent at time offset, right? Whatever this is, but it doesn't get there before C2, right? Like C2 gets there before C1, and that would look like, oh, okay, I need that diagram. So I need like A and B. There's a TCP thing here. It's a sequence, I guess, right? So if I have this message I send, and then I have this message, I needed to not do that. I have this message, and this message takes a long time, and this message doesn't take a long time. Then these would arrive at B out of order. And the only way B would know that this is out of order is if it has a 2 and it has a 1. So the TCP sequence number. So there's like a visualization of this. It's these message diagrams, but it's like this. Where is one that shows like an out of order? So that one comes in first, that one comes in second. And none of these are showing. This is just showing like the, oh, here we go. I don't know if I'm seeing any with overlapping. Okay. Oh, here we go. So interesting. TCP connections can detect out of order packets by using sequence and acknowledgement numbers. At least one packet in between. Okay, so this is like contiguous. This would be like what I'm trying to do with Lamport clocks. But right, so sequence 1, sequence 73, is there like a... Why do I not have access to these? No, this is not true. This is not true. Let me sign out. Okay. Great. Okay, so that worked. Yeah, there we go. And then just a bit less loud. Okay. So I don't know. That's all. So this would be a really interesting like update live kind of thing. And then what am I envisioning in my mind to say this? Like, I don't think anything. I don't think I'm like thinking about what the solution to this problem would look like correctly. So then it's not like a good visualization. The top right one looks good. Having out of order elements is represented quite clearly there with the line connecting the nodes, and you don't need this middle thing. It's kind of unnecessary. And then you could like highlight when like an erroneous thing is happening. So that would be good. But does that actually matter? That doesn't matter because we would have 1 and 2. So we could reconstruct a sequence. We're not missing anything. So that actually doesn't need to be highlighted. What we probably need to do is think about when events are streamed. Like the most complicated thing would be if A, B, and C messages all depended on each other. So they're adding some kind of counter. And it could be eventually consistent, but it wouldn't be consistent at any point in time if those values came out of order. So then what is the real value add here? Like, let's say we do this forever and then dot, 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 and then we get to some value, right? If that's like 42 and the answer was supposed to be 42, then it doesn't matter. And I guess the only thing is, how long do we need to wait before we get the answer? And we don't know. And if that's like, if we do a dot, dot, dot here, it's like we can't ever look at some intermediate state and know that this is working. So I think that's kind of the issue. And like, how would you know the answer to that? I guess you never really would, right? Like, you would know the best answer at the time that you knew it. So you can't know. I don't think vector clocks even give you. It would give you an understanding of, from the message you've received, like, yeah, okay. So this is time, and then this is, so there's a message from, oh great, this is the visualization. So there's a message from C, and like initialization, everyone gets a 0. C1, okay. It communicates to B, so it gets a B1 and a C1. And then the act of communicating increments B2, you have B and C. And then receiving the message increments A, so you have A1, B2, C1. So that like tells you, can you unwind this? I don't think you can unwind this. You don't know which one created the other. A2, so you increment. It would be interesting to have like a log of all of those events. So here's one. You have a B3 and you have an A2. So if you were to just receive both of these events, I guess here and here. The only thing is I'm like using a D, which is a message broker. And what would that be? That would be, we can think about C as that, I guess. So just this one isn't very good because the message broker presumably, I guess it does send it to consumers. It's just, I don't see one that is strictly, yeah, I guess you could see it as C. So, or A rather. The thing that was screwing me up was C can't send a message if it hasn't received one yet. So like A could be a good representation of the queue. So like C produces B would have to be it. It would have to be that all communications go directly to B and then B sends them out. And is that what's happening? Like A never talks to C? No, B talks to A directly there. So those need to be, those aren't good. Okay. So this like works, but here we have these two events that are fired off, and C would only know this, which is B is currently at 3 and C is currently at 2. which means 2 events occurred and 3 events occurred. And then you have the message itself. This one knows if we talk to B, that B, and then what does it know? It knows that an event is either before or equal to another event. So this is equal to itself. So if you were to ever see 2 messages that were the same here, they would be equal. And then what can we say about vectors where one vector is strictly equal to or less than? I think that means that the event must be less than or equal to. So in this case, we can't say anything because we don't have an A, B, and a C. Yeah, so that's maybe why effect is considered here. So these 2 events we can compare because we can say one event happened on C only. And then we can also say, if we look at these 2, that A had 2 events more at this point, and C had 1 event more at this point. So if we had those 2 events, we could say that A must have happened after, or message whatever happened before message whatever subtract 2. So that's interesting. So we could, if we had all of these events, like if we were to take a slice from here and say, give me your latest event, we would have A with this event and this vector. We would have B with this vector, and we'd have C with this vector. So we would say what B knows is 251, and that's less than 255. So it goes before 255. And then A has 455, which is greater in all or equal to B's understanding of the world, and it is greater than or equal to C's understanding of the world. So A would be before cheap viewers on that thing. Sounds good. So A would understand a more recent version of the world than C, and C would understand a more recent version of the world than B. And then that way you could interpret those events. So interesting. This helps you with transactions across different nodes to understand who is the most recent. But it doesn't help you understand, and you never could understand, like, what is the most recent. The only thing is that A is perceiving the most recent. Okay, so that's interesting. Okay, so I think this is a really good representation of what's going on, and then the Q just kind of gets in the way. I don't think that's too relevant to what's going on. So what do I have in pseudocode? For every interval, for each node, given some time. Okay, so for every interval, so it's really just saying that the message broker has to keep the vector clock. And then it just knows, that doesn't help. It would just know the most recent value. Can you ever really know? Okay, so let's ask ChatGPT. Or how? Kick Channel Pro 6. You stream really well. That's why I followed you. I do see you streaming a lot, and I got a proposal for you. Thanks, man. In distributed systems, can you? What do I want to know? Or how can you? with how can you ensure as a consumer that you have the latest sets of events published in a contiguous order? Okay. So that's dropping messages. Consumers commit offsets. Replay. Like, this all makes, I feel like actually I'm not missing anything. Like, if we look at this again, this is implying that everything's coming across in the correct order. That's probably not what I want to see. I'm thinking about like this. If you have the start message and it has a sequence number, so it's 1, these are state machines, that actually, the only problem I could see, and this could be wrong, is when this node goes offline and it restarts its own sequence. Like, that would be an issue. But if it doesn't, and you just have this like asynchronous period of time when C1 starts and like C2 starts and then C1 ends, you would know, because you would have C1, C2, C2. You would know at this point that you're missing an event. So I think like just having start and end messages is the answer. For this, for each node given some chance, perform an activity. The activity will take some duration. If the activity completes successfully, fire an event. Yeah, there's, okay, so I think I get this, but I think like the real thing is like on or off. So a light should be on or off, right? That's like the attack. Oh, can the Byzantine general's problem, like, I wonder what the solution to that is. Okay, so I'll probably watch this, and then I'll be back once I've watched it. All right, and eat lunch. Talk to you later.